So, good morning, Kalimera, from Hellenic Mediterranean University, the Athena European University. Together, I can see the two co-organizers with me, George Kakavelakis from EPFL and George Kavoulakis from HMU. We are very happy within the Athena European University and also the Hellenic Mediterranean University to welcome Professor Kevin Sivoula from EPFL. I will provide a short introduction about Professor Sivoula. He has received his bachelor degree in chemical engineering from the University of Minnesota in US. So he's a US citizen. He's that works in Switzerland, if I'm right.
That's correct.
He has received his PhD from the University of California, Berkeley in chemical engineering. He joined in 2007 the Laboratory of Photonics and Interfaces under the coordination and the supervision of Professor Michael Gratzel in EPFL. I hope that you remember that Professor Gratzel was our first speaker in this series of colloquia talks. In 2008, he promoted as a group leader in EPFL, and he received in 2011 a tenureship as an assistant professor. Nowadays, he serves as an associate professor. His research topics include photochemistry, organic semiconductors, 2D semiconductors, solar energy conversion, nanomaterials for energy. His work has received more than 23,000 citations. His H index is 66. And today, Kevin, Professor Sivoula, he's going to talk with us about semiconductor photoelectrodes and photocatalysis for solar-driven water splitting. If I have done any mistake, excuse me about my accent. It's very Greek, I think, but the floor is yours, Kevin, and thank you so much.
Thank you very much for the kind introduction. It's really my pleasure to be here with you this morning, and I'd like to take this opportunity also to thank all of the organizers for the chance to present some of our lab's recent work on exactly this, solar-driven water splitting. So everybody can see my screen? It's okay? Yes? All right. Well, then let's just get right started. The motivation for the work is really the conversion of renewable energy into chemical fuels. And in the future, with when we exhaust all of the fossil fuel supplies, we'll need ways to convert renewable energy into chemical fuels for use in industry and for use in the transportation sector. One of the most promising molecules for this, of course, is renewable or green hydrogen, which can be made by the splitting of water into hydrogen and oxygen. And there are different ways to do this, but one of the ways that I'm quite interested in is using our most abundant renewable energy source, and that's solar energy, right? So can we take solar energy and split water, converting it into hydrogen? If we can do this on a large scale, then we can one day use this renewable hydrogen as a feedstock, for example, together with carbon dioxide to do reverse water gas shift and Fischer-Tropsch reactions to make renewable liquid fuels for the transportation sector. You know, hydrogen is extremely important in industry today, for example, to make ammonia for fertilizers and for the reduction of materials for metals. So we hope someday, if we can find inexpensive ways to do this, that green hydrogen can be really a keystone in a renewable energy economy. But to do this with solar energy, well, we need to think about ways to do it. We can do it already with photovoltaic cell plus electrolysis cell. So today we can take a regular photovoltaic cell, hook it up to some electrodes, oxidizing water at the anode and reducing water at the cathode to make hydrogen gas. We don't do this at any large scale today, and that's because the cost of the hydrogen that's produced is still 3 to 5 times more expensive than hydrogen production using methane gas with methane reforming, methane reforming. So that really motivates our work to try to find alternative approaches for the direct solar to hydrogen production reactions. And we can imagine doing this For example, with a direct semiconductor liquid junction, either in a photoelectrochemical cell or a particle-based photocatalytic dispersion. So there's a lot of people that have thought about this in different ways and tried to look at the techno-economic analysis of this type of technology. It's not my expertise, but here's just one reference which suggests that, at least in some cases, even the photoelectrochemical configuration could produce hydrogen at a cost less expensive than PV plus electrolysis. That's assuming we can achieve a certain solar to hydrogen conversion efficiency, and the cost of the device, of course, is small enough. Alternatively, this particle-based photocatalytic approach, where we simply take semiconductor nanoparticles or microparticles and disperse them into water, really has an opportunity to produce hydrogen at a drastically less expensive cost. Again, assuming we can achieve reasonable solar to hydrogen conversion efficiency. So unfortunately, current state of the art with these types of particle-based systems are quite low. So the motivation really of my work is to investigate semiconductor materials. We typically use the photoelectrochemical configuration so we can understand the performance of the semiconductor material itself. But just keep in mind that our end goal will be hopefully someday to use the materials that we're developing in the photocatalytic particle-based type system. But in the meantime, in our lab, we prepare electrodes, photoelectrodes. We do prepare some photocatalysts. I'll say a few words about that. And we look at the performance of these materials. So I'll start today by talking about the photoelectrochemical cell. And just in more detail, we can imagine a simple device that consists of a photoanode, maybe a membrane to separate the gases, and a photocathode. And we have a liquid electrolyte in this cell. And upon the illumination of light, we generate a photopotential in each of the semiconductor materials in the photoanode and the photocathode, shown here with their band gap energies on this electron energy diagram. And in the photoanode, photo-generated holes should travel to the semiconductor liquid junction and at a catalytic site, oxidize water to oxygen. The electrons alternatively travel through an external circuit, traveling to the photocathode, where they're further excited by the semiconductor material in the photocathode, and photo-generated electrons travel to the second semiconductor liquid junction, reducing protons or reducing water into hydrogen. So to do this reaction, we need at least thermodynamically 1.23 volts of photopotential plus the overpotentials to drive the water oxidation reaction and water reduction reaction. So our challenge is, of course, to find materials and systems that can perform this stably and at high efficiency. Well, high efficiency has been demonstrated by a number of groups. Here's a few examples, one from NREL in the United States, where they show this monolithic gallium indium arsenide, gallium indium phosphide type of photocathode, which develops sufficient photopotential to split water and achieves 16% solar to hydrogen conversion efficiency. That was in 2017, and a year later, Caltech and others produced a similar type of device with some modified layers and achieved 19% solar to hydrogen conversion efficiency. However, the way that the methods that used to produce these types of gallium indium phosphide and gallium indium arsenide semiconductors are not so scalable and quite expensive. In fact, a device like this probably costs on the order of $10,000 per meter squared or more. So it really excludes this technology from large-scale production. Really, that's a strong motivation for our work in our lab, is to ask the question is, can we develop inexpensive systems that could be potentially economically competitive with PV plus electrolysis, keeping in mind that we need to have a relatively high solar to hydrogen conversion efficiency and good stability, but we also want to use materials and techniques to make our device that could be potentially under about $100 per meter squared. That's a target. We don't actually produce it, but we want to use inexpensive materials. We want to use widely available elements and avoid these rare materials as much as possible. We'd like to use scalable and facile processing of our materials, whether we're making nanoparticles or whether we're making thin film electrodes. For electrodes, we eventually like to use large-scale roll-to-roll processing. Any sort of solar technology on a large scale is going to have to cover kilometers on planet Earth, so we'd like to be able to make anything with extremely simple based methods. Keeping in mind, we still need to have high performance and stable hydrogen evolution at the year's timescale. So what materials are of interest for this direct semiconductor liquid junction, either in a photocatalyst or in a photoelectrode? Well, there are plenty in the field is looking at oxide materials, not just these, but bismuth vanidates, other ternary oxides are quite popular right now. Chalcogenide materials, like the CIGS type materials, tungsten diselenide. And our lab has some special experience with organic semiconductors and looking at these for a prospect in this direct solar fuel production reaction. So I won't have time to tell you stories about all of these materials today, but I'm going to tell a quick story about these CIGS materials. I'm going to spend a little bit more time on these layered 2D transition metal dichalcogenides. And then I'll finish by talking about applying organic semiconductors to overall solar water splitting. So that's kind of a little outline of the talk today. So we can get started. I can tell you a little bit about this CIGS or CZTS type system. So these semiconductors are now well known in the thin film photovoltaic field, and they're quite attractive also for this photoelectrochemical or photocatalytic water splitting reaction, also because the band gap of the semiconductor can be tuned by changing the composition of the materials. Specifically for hydrogen evolution, having a good driving force, having the conduction band above the zero versus the reversible hydrogen potential is quite advantageous. So converting the selenide to a sulfide raises this band gap and allows us to get a little bit better performance for the hydrogen evolution reaction. Moreover, these types of materials can be made by a simple colloidal formation of nanoparticles and then casting them into thin film electrodes. Unfortunately, when we do this, the electrodes don't work very well, and we had to develop a type of eutectic salt annealing to crystallize the nanoparticles here into large crystal domains to avoid, of course, recombination at grain boundaries and improve the performance. You know, the interesting thing is that we're able to find conditions to perform this sintering reaction at relatively low temperatures using these additives based on these chlorides. So these SEM images give some indication of the effectiveness of adding these additives. Without any additive, you can see the cross-sectional SEM image of our device. Here's the substrate, and then here's the nanoparticle film. But at the same temperature, we can, with these additives, you can see a large growth of the crystal grains. This creates a huge difference in the photocurrent that we get for the hydrogen production reaction. So this is the first time that I've shown one of these LSV or linear scanning voltammetry curves. So I'll just take a second to explain it. So on the x-axis here, we have the applied potential. So in the lab, we're testing one of these photoelectrodes at a time. and we hook it up to a potentiostat, we vary the potential, and we measure the photocurrent under intermittent illumination. So you can see the red curve here going up and down. For a photocathode for hydrogen production, we want a large negative current density. And so when the light is on, we have the current here. And then when the light is turned off, it goes back to zero. That's also showing us that we have this photocurrent effect. So we can see a big difference when we use this antimony treatment versus the black curve, which is non-treated, which has essentially no photocurrent. We can already see the effect of this grain growth in these systems. Moreover, we can finish the device by adding an electron extraction layer, a protection layer like titanium dioxide, and then a catalyst layer for the hydrogen evolution reaction, and achieve now results in this paper which were very similar to CVD processed CIGS or CIS films, with a photocurrent of about 8 milliamps per centimeter squared at 0 volts versus RHE. So that's like the short circuit current, if you're familiar with the photovoltaic cells. Moreover, this device is quite stable for a long operation in the lab and produces hydrogen at a Faradaic efficiency of 100%. So back in 2016, we were quite excited about this result, but actually something more interesting popped out to our attention, which was that even these films without any of these fancy overlayers, without the TiO2, without the CDS or the platinum, they already showed some activity for the water reduction reaction here shown in this red curve. And that has inspired more recent work where we've studied the surface of these bare films to try to understand what site is actually catalytically active for that water reduction reaction. If we can figure that out, perhaps we can eventually use these nanoparticles also one day in photocatalyst type systems. So we've used techniques like electrochemical impedance spectroscopy to identify the surface states on these bare CIGS surfaces, which we can attribute to driving either the recombination or the hydrogen evolution reaction. In fact, using techniques like operando Raman spectroscopy, and changing the applied potential where we have hydrogen evolution, we actually can see the introduction of the gallium hydrogen bond, which suggests that a gallium site on the surface is actually responsible for the catalytic hydrogen evolution reaction. In fact, if we put these two results together, we can come to the conclusion that avoiding the formation of these gallium vacancies is really crucial to achieve the high activity in these sort of films. So work goes on to try to understand if we can't achieve higher performance with these bare CIGS films and use them eventually in these photocatalyst type systems. But the drawback here, of course, is the very high overpotential that we need. You can see here our short circuit current at 0 volts is only about 1 milliamp. And we need to apply a higher potential to get all of the carriers out. So more surface engineering will be needed to make these types of materials useful for high efficiency hydrogen production. Okay, I can switch gears a little bit to a related system. Another system that's been in development in our lab now for a few years, and that's based on these transition metal dichalcogenides of the form MX2, for example, molybdenum sulfide or tungsten diselenide. So this class of materials has been known for a long time as promising materials for solar energy conversion because they're essentially earth abundant. They have good band gaps for solar energy conversion, high absorption coefficients, and they're really, really stable. In fact, molybdenum sulfide is used as a high temperature tribological material, in particular because of its layered structure. It has lubrication properties as the layers can slide past each other when they're under high shear stress, similar to a material like graphene. So the high stability and the good band gap had led people in the 1980s, especially to investigate these materials for photoelectrochemical and photovoltaic energy conversion. And in fact, those early works showed quite promising performance with conversion efficiencies here close to 8%. But the drawback was that only single crystal devices could work. So polycrystalline devices made from these materials fared very poorly, and making single crystals proved very difficult over large areas. Here's a few examples of single crystals that you can even purchase of these materials, but they're extremely small. So making large area single crystals and the difficulty to do that basically meant these materials were probably not viable for large area solar conversion. Now, recently, a little bit more recently, Nate Lewis's group at Caltech showed that a tungsten diselenide photocathode material performed exceptionally for the hydrogen evolution reaction. What they did was take a single crystal tungsten diselenide and they put a catalyst on it, like this platinum ruthenium, and they showed short circuit photocurrent densities under one sun of almost 25 milliamps per centimeter squared. That's compared to the sort of 8 milliamps that we had with the CIS photoelectrodes that I showed before. So the performance is really, really good. The quantum efficiency is shown here. The high photocurrent is partly given to the relatively low band gap of this material of around 1.4 electron volts, but also to the high quantum efficiency of about 60% in this system. But again, the fact that this is a single crystal makes it difficult to imagine this over a large area. So that's when our group became inspired by the layered crystal structure of these types of materials, which allows the exfoliation into two-dimensional or few-layered type nanoflakes or sheets, which have been shown by many groups to have exceptional optoelectronic properties in many different types of optical sensors, even photovoltaic devices here. But if you know about this field, typically, these flakes are produced by the Scotch tape method or mechanical exfoliation, leading to essentially devices on the size of a micron or a few microns squared. So again, using this for a large area solar energy conversion maybe isn't so viable. Our lab wanted to find a way to coat over large areas these types of nanoflakes or nanosheets, so we could eventually demonstrate large area hydrogen production using these types of materials. And to do that, we borrowed a method that was developed by John Coleman in Ireland, where you can make nanosheets of these materials by just taking a bulk powder. So we can buy a bulk powder of, for example, tungsten diselenide from Sigma Aldrich at a 10 mesh size. And we can put that in a suitable solvent like NMP and put it under ultrasonication conditions to essentially exfoliate the material into nanoflakes, dispersions in the solvent. So this is quite promising because with a nanoflake dispersion, perhaps we can coat this over a large area and see high performance solar energy conversion. Now, here's a SEM or TEM image of a type of a flake that we get out of this type of approach. It's not perfect. It's not a single layer. It'll be multi-layers in some cases. It's kind of got some raggedy edges, I would say, that I will talk about in a second. But there's a lot of advantages when it comes to performing this solution-based or liquid-based exfoliation techniques. However, when we try to make films of this over a large area to test the photoelectrochemical performance, we ran into a big problem. And that's when we tried to remove the solvent, the van der Waals forces between these large area basal planes causes rapid restacking and aggregation of these flakes and really makes poor films. Here's an optical image of a film that we made by just drop casting some exfoliated tungsten diselenide. You can see these big aggregates by SEM, you can see perhaps more clearly. The issue here, of course, is that our semiconducting basal plane is not in good contact with the transparent conducting substrate, meaning that we have very, very poor performance. We tried many different techniques to optimize a deposition of these nanoflakes, including floating the film at a liquid air interface, which still didn't work. But I had a very brilliant PhD student who figured out that we could use flake self-assembly at a liquid-liquid interface. So I'll just show you a video here quickly. We inject the dispersion of the nanoflakes at an interface, for example, of hexane and ethylene glycol. And since our solvent here, NMP, is soluble both in hexane and ethylene glycol, the solvent goes quickly into those phases, leaving the nanoflakes to want to minimize their energy and align at that liquid-liquid interface quickly. Then we can simply remove the solvents, depositing the film on a substrate that's waiting. A small heating to remove any residual solvent leaves us with a nice film of our nanoflakes of tungsten diselenide. Now, the good part about this technique is that we can do this on flexible substrates at low temperature. We don't need any high temperature processing. However, we have to note that by TEM image here, we do have still separate flakes that are in good contact with the transparent conducting electrode here. So this is an advantage of this technique. However, even using these directly for solar hydrogen production gave very, very poor performance. And that's due to these edge sites, which have a lot of defects that serve to recombine the photogenerated charge carriers. In fact, this is well known about these tungsten diselenide type films, and it's one of the reasons why the polycrystalline photovoltaic devices didn't work very well in the 1980s. And it's also due to one of the problems with these materials is that they have a very anisotropic charge carrier transport. So given the crystal structure here of the material, if we look at a typical single crystal surface, it'll even have these step edges. And these step edges here represent defects, for example, like the selenium vacancies here, that will cause recombination. Now, again, the charge carrier transport in this direction along the flake axis is about 1,000 times greater than it is in the direction parallel, which means that photogenerated electrons are more likely to travel very fast towards these edge sites and recombine. So in order to reduce this recombination, we later developed a passivation technique using an organic hexyl trichlorosilane, which can plug some of these selenium vacancies. And this led to improved performance for hydrogen evolution. That's shown here. This is without the HTS treatment. And with the HTS treatment, we've improved the photocurrent by about a factor of 4. Now we're getting about 4 milliamps per centimeter squared photocurrent for hydrogen production out of these electrodes. But it's important to note that we're very, very thin. These layers are extremely thin. We're not absorbing light like a single crystal. So when we account for the light absorption in these films and calculate the absorbed photon to current efficiency, that's shown here, in the purple data, we see we have quantum efficiencies that are about 50% over the wavelength that the tungsten diselenide absorbs. That's compared to the 60% that was achieved with the single crystals. So simply using this exfoliation technique, followed by this deposition technique and the passivation technique, we're able to achieve solar to hydrogen conversion quantum efficiencies similar to the single crystals, which are very difficult to make. I should note that to achieve the hydrogen evolution, we put a platinum copper-based co-catalyst on the surface, and we can measure very stable performance, and we can use a gas chromatograph to measure the hydrogen coming off to show that it's 100% Faradaic efficiency. So to kind of extend this work and even improve the performance, we've done a lot of investigation on the effect of the, for example, the flake size. So in this work, we used track etched membranes and this sort of filtration system to isolate samples of these tungsten diselenide nanoflakes at different sizes. And together with an understanding of the sacrificial and hydrogen evolution performance of these different sized flakes, we were able to develop a model of charge carrier transport and recombination that gave us some insight into the limitations of the performance of these flakes. So let me just expand on this for a second. If we imagine the cross-section of a flake like this, and light can be absorbed at any part of this flake, generating electrons, which we want to travel to the basal plane to reduce, for example, the protons to hydrogen. However, if those photogenerated charge carriers are generated too close to the edge where the recombination can occur, then they'll more likely be transported and perform the recombination. So based on our experimental results and our drift diffusion model, we can predict the quantum efficiency here depending on the flake size, either the thickness and the flake width. Now, clearly from this, we want to achieve nanoflakes that have very large lateral dimensions and very thin thickness, so only a few atomic layers, to achieve the highest quantum efficiencies. However, this sonication-based exfoliation that we use always gives us flakes that sort of live along this line. And that's due to a basic mechanical relationship between the Young's modulus of the material in the A direction and the C direction, which causes a fracture of the flakes during this ultrasonic exfoliation. So we're not able to achieve very, very large flakes that are very thin. Well, if we could do that, we would expect to achieve higher conversion efficiencies. So we found a method that would allow us to do that using what we call electrochemical pellet intercalation. So again, we just take some commercial available powder and we press that into an electrode. We anneal it a bit to increase the crystal size and the conductivity. And then we intercalate a large cation molecule here. This is an alkyl ammonium bromide. So the alkyl ammonium will intercalate into the flakes and exfoliate the flakes without causing a lot of damage and without breaking the flakes as much as the ultrasonic approach. Then we can isolate a large, relatively large flakes with fewer defects. And that's shown here when we compare electrochemically intercalated flakes here, much larger and thin with pristine basal plane compared to the ultrasonicated flakes, which you can see have a lot of step edge defects, layer fractions, and have well, just a messy looking surface here. So the best results we have on this are on a slightly different system where we used molybdenum sulfide and we have a sacrificial photoelectrochemical reaction. But comparing the ultrasonicated flakes to the electrochemically intercalated flakes, we see a huge difference in their absorbed photon to current efficiency. Now we're achieving almost 90% of the photon conversion efficiency based on the absorbed photons in these electrochemically exfoliated flakes. So moving this towards tungsten diselenide and demonstrating hydrogen evolution with this technique is currently underway in our lab. In addition, like I said in the introduction, we're quite interested in understanding how we can make these types of films over a large area. And one of our industrial collaborators challenged us to really demonstrate a roll-to-roll processing using our liquid-based self-assembly method that we developed. And just a short interlude here for fun, I show you some pictures and a video. We actually did this. Using a 3D printer and a stepper motor, we're able to develop this system where we can inject our flake dispersions here from the bottom. And here's our liquid-liquid interface. The nanoparticles assemble at this liquid-liquid interface, and then we push the film towards this substrate, which is being extracted here. And there's another view of it a little bit better. This is sped up 4 times because we have to do this a little bit slow and careful. And at least in principle, we can put this, we can use ITO-coated PET substrates and show that the film that we make has similar performance to the small-scale films on glass. It's not perfect. Listen, if we wanted to optimize this and better machine it, we could get rid of some of these cracks and defects. But I think for a first demonstration of a large area roll-to-roll processing with this step, I think we have definitely achieved that. Okay, so we'll hopefully be able to use these materials if we can get the performance up a little bit better. And for example, use some tricks like heterojunction formation to increase the photopotential to make overall tandem cells for water splitting, or use these as photocatalysts for the particle-based systems, as long as we can passivate all the defects effectively. And if I switch gears a little bit and talk for a second about that photocatalyst type approach, as I mentioned before, I'm really inspired by this approach, given its simplicity, right? Simply taking a nanoparticle dispersion and putting it into water in a plastic bag or a pond out in the desert and producing hydrogen really with a technical ease. But today, like I said, the performance of these systems isn't so good. And for example, here's a Z scheme, bismuth vanadate, tantalum oxynitride scheme, which only gives about 1% solar to hydrogen conversion efficiency. And it's really due to the poor charge separation. In a typical photoelectrochemical cell or a photovoltaic cell, you're probably aware, we have some driving force for the charge separation, whether that be the use of electron extraction layers or a PN junction. And that's very difficult to implement on the nanoscale in a particle. Now, there has been some examples of that. For example, like Doman's group in Japan has shown that these faceted strontium titanate nanoparticles have slightly different surface energies, which causes an electric field, which can actually effectively separate photogenerated electrons and holes in the nanoparticle itself. But a material like strontium titanate is quite high band gap. So again, the overall solar to hydrogen conversion efficiency is only about 1%. So one challenge in the field of heterogeneous particle-based photocatalysts is to develop systems which can separate effectively the electron and hole after they're photogenerated, but also have materials that absorb a lot of light. There's one system that caught our attention as being capable to separate photogenerated charge carriers on this sort of nanometer scale, and that's the organic bulk heterojunction type systems. So you may be familiar with the organic photovoltaics that typically use a blend of a donor and acceptor material like this, and that blend is made on a sort of a nanometer link scale or a bulk heterojunction in the active layer of a device like this. And the intimate contact between the donor and acceptor is necessary because upon light generation, for example, in this P3HT semiconducting polymer, a free electron and hole is not produced. Given the optoelectronic properties or the electrostatic nature of these materials, we produce a bound electron-hole pair or an exciton. And only when that exciton can reach an interface with an electron-accepting material like this fullerene can we separate charges into the free electron and hole pair. And because the exciton diffusion length is only on the order of 10 or 20 nanometers, this intimate contact between the two phases of the donor and the acceptor needs to be on that length scale. But this technology is already developed in the thin film and is quite interesting for photovoltaic energy conversion. It's been developed by many groups over many years, with over now 18% photovoltaic or solar to electricity conversion efficiency, we are inspired by using this concept for the photocatalytic type of approach. So we can imagine if we can sort of miniaturize this bulk heterojunction into a bulk heterojunction organic photocatalyst, one for evolving hydrogen, one for evolving oxygen. We can imagine both of these particles absorbing light, the heterojunction separating the charge, and overall we could hopefully achieve efficient charge separation, leading to efficient solar to hydrogen conversion. Now, we weren't the first people to think about this. In fact, Costco and Ian McCullough's group at KAUST has some really good demonstrations of this concept for the hydrogen evolution photocatalyst. Now, this is quite interesting in my mind. I'd like to see this concept work for overall water splitting, but there are a few open questions. One, can these organic semiconductors be stable in the harsh conditions when we put them directly in water and ask them to produce hydrogen or oxygen? And two, well, this has been demonstrated on this side, but could we get an oxygen evolution side also to work? So we're quite interested in answering both of these questions. And while I can say that we are making these photocatalysts in our lab, we want to better answer these questions with the photoelectrode approach, because we can gain more insight into the performance of these materials, especially the stability. For example, other groups have looked at photocathodes of these organic semiconductor materials for hydrogen evolution and have seen a very poor performance here. Only after an hour, the photocurrent drops by a factor of more than 2. This was also demonstrated, a similar demonstration by another group, which showed a similar decrease in the photocurrent after only about 1 hour. And they attribute this somehow to the delamination of the platinum that's used as a catalyst on the surface. However, I think it's not clear whether these materials themselves, these organic semiconductors, could be stable under these harsh conditions. So we started a project a few years ago just asking a simple question, can a direct semiconductor water junction be stable when we use these organic semiconductors in the bulk heterojunction format? And we used a very simple system. Instead of making hydrogen, we just put a bulk heterojunction directly in water and asked it to reduce europium here, this europium 3 to europium 2, which should be a simple 1 electron transfer, sacrificial type of reaction. We first looked at this with these two materials as a donor and an acceptor, which have a little bit higher performance than the other materials that were shown on the previous slide. And while we do see some reasonable photocurrent here under these sacrificial conditions, when we try to run this as a function of time, the photocurrent quickly degrades down to 0. In fact, for us, in only 10 minutes, we see a very poor performance. Now, we took some inspiration from the literature of the organic photovoltaics, which suggested that these fullerene-based materials aren't so stable. And it turns out that that stability gets worse when we put them in water. If we just change this material, for example, for this PDI-based polymer, we get much more robust performance. First of all, a little bit higher photocurrent with this PDI, and then much more stable performance. In fact, we have a little increase in the photocurrent, in the absolute magnitude of the photocurrent, because the film has a little bit of water ingress over the first 20 minutes, which actually helps the surface area for the reduction reaction. Now, I'm probably running out of time, so I don't have time to explain all of the detailed photoelectrochemical results that we have performed on these films. But the long story short is that we've identified the limitations of stability of these photocathodes due to an electron accumulation at the bulk heterojunction interface, which causes chemical damage, which we can see here by the FTIR before and after under certain conditions. And using electrochemical impedance spectroscopy, we can actually quantify the amount of charge accumulation. we know that if we can keep the charge accumulation low on the order of 100 nanocoulombs per centimeter squared, that we can achieve good stability with the performance of these photocathodes. So reducing charge accumulation means that we have to put a very effective catalyst that can drive the hydrogen evolution reaction on top, and also make sure that that catalyst is well coated and well adhered to that organic film. We've achieved the best results with this ruthenium oxide-based HER catalyst, which has a better adhesion compared to platinum on the surface. And overall, we've achieved quite good stability for about a day, only losing 33% of the initial photocurrent of the photocathode. And that's still probably due to some of the catalyst layer falling off, as shown here on the SEM. But overall, this performance is quite nice for a photocathode. And we can do this over a large area. We can make simply solution processed photocathodes, which can make hydrogen here under illumination with an applied bias with this organic based light absorbers. And the last part of the story then, as we've shown, we can make hydrogen with these organic semiconductors. Can we also make oxygen with a photoanode with these organic semiconductors? This proved to be quite difficult. Not only do we have to find organic semiconductors that have the right energy levels to oxidize water, but also can be reasonably stable under the harsh conditions. We haven't done great at that, but we have identified a system based on these two polymers here as the acceptor and the donor, which do have the appropriate energy levels for water oxidation. And we had to play some tricks to get this to work. For example, using a mesoporous zinc oxide electron transport underlayer helped to improve the stability. I won't go into that, but you can look at the results that were published recently. And secondly, applying this PTAA overlayer, which really helps to quickly extract the holes to reduce the hole accumulation in the bulk heterojunction, which proved detrimental to the stability. Finally, by applying a lithium-doped iridium ioxide OER catalyst, we were able to demonstrate overall, or the water oxidation reaction occurring under illumination in these photoanodes. The effect of the PTAA is shown here on the ability to shift the LSV curve here a little bit in the cathodic direction, giving us more potential. But it's more importantly shown here where we achieve better stability, especially in the initial operation of this photoanode. Without the PTAA layer that extracts the holes, the performance drops very quickly. But with the PTAA layer, we extend the performance at least for a few minutes before it starts to drop off. And again, we can measure the quantum efficiency and the gas production here to show that we have a high Faradaic efficiency, close to 100% for the oxygen evolution, at least in these initial stages. And as a final step, we can put everything together, our photocathode with bulk heterojunction organic semiconductors, our photoanode with our bulk heterojunction organic semiconductors. And we had to do a little tweaking here because the underlayer we used for the photocathode in the previous work wasn't stable at the pH 9 we're using for overall water splitting. But after that, we were able to demonstrate unassisted overall water splitting at a solar to hydrogen conversion efficiency of only about 0.5%. So a very modest demonstration here. But the first time that this was ever done with organic semiconductors, both in the photocathode and the photoanode. So I think I'm probably running out of time. So let me stop there, conclude, and I hope today you've seen that we can use sort of these inexpensive solution processable type semiconductor materials to drive the overall water splitting reaction using a photocatalytic or photoelectrochemical type techniques. The key take-home messages that I want to give, of course, and it goes without saying, whenever we have semiconductors and solar energy conversion, that defects and surface states are really critical to the operation. And it's especially important with our solution processed semiconductor thin films. We have a lot of defects. We have to deal with these. For the organic semiconductors in particular, limiting or reducing the charge accumulation in the semiconductor layer and preventing any parasitic reactions that can occur will be important for achieving long stability with these systems. And even optimizing the mechanical and electronic aspects of the interfaces, not just for defects, but just for increasing stability and for extracting charges is really important for these overall systems. So with that, I certainly have to thank the people that did the work. Some of them are shown here, external collaborators, funding for this work from the many sources. And I'd like to thank you for your attention. Happy to answer any questions or have any discussion that you'd like on this material. Thanks again.
Thank you very much, Kevin, for this very nice presentation and your enthusiasm. It was really nice. If you can please stop sharing your screen in order to so are there any questions to the audience first? If you have any questions, please raise your virtual hand and direct, your question to Kevin. I'm waiting for the audience, and otherwise I have some questions. Okay, Peter, the floor is yours.
Okay, thank you for the really wonderful presentation and very nice overview. In the beginning, you stated very nicely also your price tag overview of potential applications. Yeah, then you enter science, and obviously this depends on the scale up of these technologies. But where do you see key challenges or the objective which you stated? I'm not sure if I got it right. 10 euros per square meter or something like that. How far are we from there? That would be one question. And on the other side, the key challenge, obviously, surface defects have been for, I don't know, 100 years since semiconductors are there, our key problem, especially for the tungsten deselenides. Have you thought about some intelligent passivation at the flake level? Yeah.
Well, thank you for both of your questions. The first question regarding the sort of progress towards the performance and or economic goals for these systems. So our lab really tries to take the approach where we start with the types of material processing that's scalable and amenable to the large area formation, so that if we can make a system that could achieve the performance benchmarks, sort of the 10% solar to hydrogen conversion efficiency, that the sort of cost benchmark is already satisfied. That's a challenge that we impose on ourselves because the high efficiency has been demonstrated in other systems. So, I'd like to say, at least when it comes to the cost of the device, probably we already meet that cost benchmark, but the performance benchmark we don't meet yet. So again, our best systems are on the order of 1% solar to hydrogen conversion efficiency. That needs to be increased by a factor of 10 to be sort of at that level. And it's been a challenge for many years. Our materials have the light absorption. They absorb sufficient amount of light to achieve that 10%, but it's a question of getting the overpotentials lower, the photopotential up, and when it comes to a tandem cell that works together with a photocathode and a photoanode, generating the overall light harvesting and potential that's sufficient to split water. That's really limiting us at the moment. So the development of better OER catalysts will be important because the oxygen evolution reaction has a horrible overpotential. We lose 0.3 or 0.4 volts because of that. So that's another area that many researchers are working on, as you know, to improve the oxygen evolution catalysis. And further, reducing the surface states, as you mentioned, can help to improve the photopotential and then eventually the performance of these systems. Specifically about the tungsten diselenide, you mentioned, yeah, these flake, the flake defects. We have tried a number of things. There are passivation strategies that are sort of post formation of the nanoflakes or nanosheets. Pretty much all of these we've tried either in solution or on the thin film. And there is potentially also a strategy to reduce the defects before exfoliation. There's also some intrinsic defects in these materials before the exfoliation. I think we've solved that problem a bit with our electrochemical exfoliation technique, but we'll never completely eliminate the surface or I would say the edge defects. That's something that we're still working on. Our chemical passivation technique, we know, isn't perfect. It has a small effect, but based on the light absorption, we should be able to achieve bigger gains by passivating the defects. We try different types of chemical sort of functionalization of the surface. Another approach is to use a heterojunction, van der Waals heterojunction, to try to extract the charges before they can recombine. All ideas that we've played around with, but haven't, well, let's say we haven't achieved a low enough onset potential, high enough photopotential to use these in a tandem cell for overall water splitting yet. So if you have any ideas, I'd be happy to hear them.
I only hear this beautiful toys of stacked 2D materials, which could be guided along this direction, but
we're trying to get it to work right now in the lab, but we're working on that.
Yeah, but I think these visions then collide with the cost efficiency vision. Yeah, if we start getting too fancy on the 2D stacking materials, this Lego,
agreed.
Then we're in trouble.
It has to be a simple way. It's got to be some sort of self-assembly technique. But this is something I'm quite interested to do.
No, but thank you very much. Brilliant.
Thank you for your questions.
Thank you very much for the question and the answer, and the floor to Dr. George Kakavelakis.
Hello, Professor Sigula.
Hello, nice to see you again.
Thanks for the nice presentation. I would like to ask you also about this transition metal dichalcogenide materials. So, I mean, I know there is a trade-off when exfoliating this type of systems regarding the indirect to direct transition of the band gap, and also of the, I mean, due to the because you have your electron hole pairs defined in a two-dimensional system, your exciton binding energy will increase significantly. So how does this trade-off or these two parameters affect the performance of the oxygen or hydrogen evolution reaction systems?
Yes, so I think it's a really good question. I can say first of all that the films that we make, they consist of flakes of all different thicknesses. Monolayers to tri-layers are very common, and then even some thicker films. Even when we try to separate the flakes by size, we don't have a pure sample of the monolayers. I would really like a pure sample of monolayer flakes that aren't full of defects to actually test this. Even our electrochemical exfoliation technique, actually we have the vast majority are tri-layer flakes. So tri-layer flake has an indirect band gap. It doesn't suffer from extremely high exciton binding energy like the monolayer flakes. What I guess is what it will happen if we have a full sample of monolayer flakes is we have an increased absorption coefficient due to the direct band gap. The band gap's a little bit higher, but we should get a lot of light absorption. However, the increased binding energy will mean that we have to apply a higher potential to really separate the charge carriers, unless we use some strategy like a stacked van der Waals heterojunction to separate the charges. So I think a strategy, an ideal strategy, would be really to have monolayer, and on the micron-sized devices, this has been already shown that at least for photovoltaic devices, this structure is quite effective to separate the charges. Doing this over a large area for inexpensive cost is a challenge, but hopefully someday we can find a system that will do that, and we can investigate and answer better your question.
Thank you very much. Thanks.
Thank you very much for the question and the answer. And I have, a question. First of all, I would like to ask you, how do you deal in these photoelectrodes with the light pathway? I mean, photons that they can escape. How do you engineer them to reflect them back and enhance the production of, the electrons or the holes?
Good question. I think that's a stage of the device engineering that we actually haven't considered at all on our devices. We're not putting any anti-reflection layer. We're not putting any scattering layer to improve the light harvesting. That is something that I think on the next level of device engineering could be implemented to, especially on the 2D nanoflake or nanosheet type films. We're not absorbing a lot of light. We're absorbing 20% of the light if we just have a film and the light is incident. So finding ways to improve the light absorption while also keeping a good contact with the substrate, so using reflective layers or scattering layers, is a really great suggestion that we haven't yet done. So future work.
Thank you. And second question that I have is, like, a part of the thickness that you gave, a very nice graph, the balance of the thickness and the
flake size, the width.
Yes,
yeah.
Exactly. What about dynamics, time dynamics? How fast, this electron they can escape, or the holes they can escape. I suspect that this is to do with another comment that you mentioned, that the polycrystalline crystals, they fail. Am I right? And you use zinc crystals?
Yeah.
Okay.
So yeah, I mean, we don't typically measure the transients of individual carriers. We assume that, and in our model we assume steady state operation. So we have a steady state production of electron holes and then drift and diffusion. But the timescales of the transport are important, as I hope I tried to mention. But the fact that the charge carriers have a mobility that's 1,000 times greater through the basal plane, in the direction towards the defects, compared to in the C direction out the basal plane, really, implies that disagreements between the timescales for the transport of the charge in the basal plane and out and are orthogonal to the basal plane. So I think if I understand your point, yes, the timescales are important. We sort of have some implication of them, but we haven't measured them directly through transient transport measurements in these systems.
Thank you very much, Kevin. Thank you very much for the answers. I think that, with the permission of Peter Bolivar, probably, Kevin's group in PPFL could be an excellent associate partner in our new Moodus program.
We would be honored.
Yeah, I will send him an abstract of the idea.
Send me some more information.
Yeah.
Excellent.
So thank you so much to be with us. Kevin, thank you very much for this excellent talk. I would like to thank also, for the participant, also George Kakavelakis, for the suggestion to be among our colloquia talks. It was really, really nice. We are going to renew our colloquia talks meeting next week. We are going to have a speaker from Hellenic Mediterranean University who is going to speak about perovskite solar cells and modules and how do they run, the first perovskite solar park in Crete. So until the 9th of December, if we don't have any other talks in the between, I would like to thank you, stay safe, and speak you in a week. Thank you very much again, Kevin, for this nice introduction,
Yeah.
and all of you
Thank
for
you
the
very much.
participation. Bye.
Have a good weekend. Bye-bye.
Bye.